Whether AI can be truly sentient is a different question from whether it can reason at a human level or achieve artificial general intelligence. This short video will demonstrate why it is impossible for machines to be sentient or self-aware, using the simple idea of finding true randomness. Let's say you want to listen to your song playlist in a random order, so you enable the shuffle button on your music player. Are the song selections truly random, or is there an algorithm behind it that determines the next song for you? For example, a simple pseudo-algorithm might be written like this. When next is clicked, or a song finishes playing, choose the next song from those played within the last 100 hours, or select one randomly using a random function with playlist IDs. This random function is a common feature in most computer languages. It fetches data and generates a choice randomly. However, it is just another piece of mathematically written code created by the people who developed that computer language to produce pseudo-random numbers. Going deeper, that high-level random code is translated by an interpreter into the lowest-level language, the machine language, in binary, zeros and ones, so that the machine can understand and perform calculations. These binary calculations or executions happen at the hardware level where transistors and logic gates come into play. Although transistors can be used as amplifiers in analog systems, we'll think of them as simple on and off switches and focus on the digital world for now. Let's see how they store those binary codes as zeros and ones while following the simple switch concept. Rather than manually pressing a switch to allow current to flow, a transistor is triggered to an on or off state using voltage. This on state can represent a bit of information as a 1. This one bit of information can be remembered using a simple and clever arrangement of the logic gates like this. And with additional circuitry, even more useful behaviors can be achieved. This allows specifying which value to store using a single input. Here, when the write enable input is set to 0, the value in the data signal is completely ignored and nothing happens. But when the write enable input is set to 1, the circuit retains whatever value is being passed to the data input, and the value persists even when the inputs are set back to 0. And later, when it is necessary to overwrite the value stored in the circuit, all that is required is to activate the write enable signal, while inputting the desired new value to store, in this case, 0. A read and write memory has been successfully created. This circuit can now be abstracted into a component called a gated latch. Here, if the write enable input is set to 0, no action will occur. But if the write enable input is set to 1, it will retain whatever information is being passed from the data input. With just that single bit, basic data like 1 or 0, true or false, or black or white can be represented. But that's it. If the aim is to represent a broader range of numbers or a larger set of colors, a single bit becomes insufficient. However, multiple bits can be used. Like this 8-bit register with 8 latches that can store a byte of information. This method requires a lot of wires to upscale, so they can be arranged in a matrix structure. Here, decoders can be added for address selection of a specific latch. With some additional modifications, each latch can remember its own value. This is just an oversimplification of how data is written, read, and stored in a machine. Similar principles can be applied to components such as flash memory for storing permanent data like music files, RAM for temporary storage of recently played song data, and an ALU system for performing calculations, such as selecting the next random song. So by understanding it at the fundamental level, we can now just appreciate the higher levels of abstraction that account for efficient address storage, speed, and storage capacity. So the digital world is simply positive and negative electrical charges arranged on a board in a clever and complex way to represent numbers, pixels, motion pictures, sound, and everything else. Thus, true randomness cannot be found in the digital world. It will always come down to 0 and 1, the on and off state. And by the way, like digital computers, analog computers cannot produce true randomness. Both are deterministic. The main difference is that digital systems are discrete, while analog systems are continuous.